please join me to welcome Dr. Hao-Wen.
Yeah. Thank you so much for the introduction. So yeah, so today I will be talking about generative AI for music and audio. I think the goal is try to give us an overview of what's going on in the field of generative AI. And also you've seen a lot of application for generative AI for in the image domain and other domains, but what's going on in the music and audio, that's what I want to share in this talk. Cool. Let me see. Okay, it freeze. Cool. So before I started, let me introduce a bit about myself. So I'm currently a PhD candidate at UC San Diego. And before that, I was doing a research assistant with Dr. Yishun Yang, who is now a professor at National Taiwan University at Academia Sinica. And before that, I was doing my undergrad in EE at NTU. And during my PhD, I've also done a lot of internships at different companies. So you will also see some of my internship projects later in the talk. Cool. So before we started, I want to show you what's going on in generative AI. So this is a video that's generated by AI. That's
Mumbai.
Sorry, it's too loud.
Mumbai, the city of dreams. But this is not the Mumbai you once knew. Now it's the cybernetic heart of India, where drones are the new rickshaws, and the sky is a swarm of them carrying people. The bazaar has always been the pulse of Mumbai, where people come together. But it's just that, now we trade, in tech. The sea and the slums, they remain, but they're different now.
Yeah, so as you can see, it's very impressive. Firstly, the visual, the image are generated by Midjourney, and then they use the runway, which is a image to video generator. So once you have the image, you put it into the runway, it will generate from stable image to a motion picture animated image. And the narration, the text here, is actually generated by ChatGPT. And then they use the 11 Labs, which is used to do the text to speech synthesis. So basically, most of the things are generated by AI. And also the sound effects are generated by Audiocraft. But the music itself is not generated by AI. That's why it sounds really nice. But as you can imagine, in the future, we will see more and more applications there where we can see how we can use AI to generate everything using AI. So what is generative AI? So this is the definition on Wikipedia. So basically, it's an AI capable of generating text, image, or other media. And so this is through machine learning mostly. So basically, you look at a lot of training data in different domains, and then you try to learn to generate new stuff. And there are a lot of different applications. And as you may see, lots of application in generating image, and also what I did in music generation. And also there are other applications in finance, and also in healthcare. For example, in healthcare, many doctors are already using ChatGPT to write their medical records, because it's a super time-consuming process, and most of the texts are not essential in practice. So the doctors just use ChatGPT to generate the medical record, and they just fill in the keywords. Cool. So you may probably already know some of these. So we've seen a lot of success in visual arts. So first, like we also have like AI making the magazine cover for a super famous magazine, and also in the middle we have this art contest, which is in Colorado. I believe it's like a Colorado fine art competition, and so this painting or image is generated by AI. I think it's Mid-Journey, and it actually won the first prize in one of the categories. And at the right, you see this like photography contest, which is the Sony World Photography Competition. And also this image is also generated by AI, but it actually won one of the first prize in one of the categories. So yeah, so there's a lot of applications in visual arts. And now we jump into the audio side. So before jumping into what's going on, I think I want you to listen to this audio samples and try to figure out what's going on in audio. And there are three types of typical objects that we are aiming for when doing audio research.
Area seems to be clear. There's a metal shack.
So yeah, as you can hear in this example, the first thing you hear is like the sound effects, like the grass scratching sounds, and then you hear the dialogues, and also at the background we have the music. And so this is basically three types of audio that we typically, when talking about audio research, that we are focusing on. So first, speech, and also music and sound effects. And for me, my research is mostly on music and sound effects. And so today I will focus on these two categories. And I want to point out that sound effects is actually different from what you might think of in professional production. So in professional film production, actually the sound effects are not recorded in real life. It's like when you are filming the movie, you actually discard all the audio that you record at the site. And so there's a job called Foley artist. So basically it's trying to reproduce everything happening in the movies. For example, like here we have I think a basketball or bowling ball, basically drop on a sand. And so these type of sound is not recorded on site mostly. It's actually recorded again in the Foley studio. And so you can imagine, like, if we have generative AI for sound effect generation, it would be super helpful, because otherwise you have to basically go through this process to generate all the recreate all the audio you see in the movie. Cool. And so here are some examples of like generative AI for music. So these are super latest development. I think it's like less than 1 month old. And so basically now we can do something like text to music generation. So here we have the prompt and we can generate the sounds. These images are just Google images. So let's listen to some of the examples. Yeah. So yeah, as you may see, like the recent text to music system are working super nice. And also we have okay. Oh. Cool. So also we have like sound effect generation system. So at the left, we have the text to audio synthesis. So basically we have some prompt like whistling with wind blowing, and you want to generate the sounds. And this can be used for in the like Foley setting or like movie production, or even like show video production on say YouTube or TikToks. Yeah, and we also have like image to audio synthesis where we have the image as the input. And so this is one of my research that I will introduce later. Yeah, so you can probably imagine like how this can be applied in like film making. Like you have a video track and you want to add audio to that track, and so this can be used for through using text as input or image as input. Cool. And so yeah, so before doing like all these like generative AI thing, I actually started from music information research. And so this is quote from Eric's lecture note. So basically MIR is like music information research. We can define it as like intelligent ways to analyze, retrieve, and create music. So yeah, just give you an overview of like what's in MIR. And so the first thing we did is like in analysis. So like music classification, genre classification, or like emotion recognition. And we also do like retrieval, which is like the most profitable application is in recommender system, which is used intensively in Spotify, Apple Music, and like Amazon Music. And finally, we have the creation side, which cover a wide range of application like automatic composition, automatic accompaniment, and also like style transfer or audio synthesis. And so this is the part that I will focus on, and that's one of the main topic of my PhD research. Cool. And so I guess like MIR is like a cross-disciplinary field. And so it covers like double E side, having like signal processing part of it. And also we have the musicology and like music theory part. And also most like recently we have a lot of like computer science based like deep learning and machine learning. And also notice that these images are actually generated by Adobe Firefly. And so it's like a latest text to image generation model, which is it's not open source, but I mean, you can use it online. And so basically you can create something like a cat playing heavy metal. You can probably imagine like you probably won't have this example in your data set, but somehow the model can magically learn to generate a cat playing heavy metal. So that's the power of generative AI. And yeah, so my research, this is like an overview of my research. I will go into some of them later in this talk, but just to give you a quick overview of what my research is about. So the first topic that I do is multi-track music generation. So basically it's like generating new music from scratch automatically. And so the first project that I did is called MuseScan. It's like back in 2018. It's like 5 years ago, almost. Yeah. So it's a bit outdated. So as you can hear, like it's like 5 years ago. And like in the last 5 years, we already advanced stuff super quickly into the examples I showed earlier. So yeah, and this work is like one of the first work that actually work on multi-track music generation using deep learning. And also it has like been featured in Amazon AWS Deep Composer. And yeah, it's super cool to see it actually implemented into one of the real keyboard that you can use. And more recently, I've also published a paper on ICAST 2023, and it's called Multitrap Music Transformer. So basically using transformer, a more advanced or more recent model for text generation. And so we applied it to multitrack music, and we will discuss this later. And the second part of my research is assistive music creation tools. So now we are not generating the music from scratch and just like pure automation. Now we are trying to assist humans to create and perform music. So I will show you 2 examples of what it's like. So the first project is called Arranger. It's published in Izmir 2021. And we are basically working on an application called automatic instrumentation. So basically what it means is like we may have like a piano or a guitar input, which is just one single solo instrument. And we want to generate an ensemble, like a pop band or like an orchestra based on the input that you have. So it's just like framed as a super simple machine learning model, but it can actually generate something really cool. So here we have the input, which is played by a guitar. And so we can turn it into like a multi-track music. Yeah, so this can be used for like helping musicians to do arrangement or doing other things later in. So it can be basically integrated into the professional creation workflow. And the other project is called Deep Performer, which is a score to audio synthesis. So basically we are trying to go from the original sheet music directly into the waveform at the end. So here are some examples. Yeah, and yeah, so the idea is that we want to make it more natural. It's not like fixed duration per note. It actually will assign different lengths to each note in the sheet music based on the pitch. Cool. And the final part of my research, like the most recent research, is multimodal learning for audio and music. And I think this line of research is like only possible in the last few months, because like we have seen like Clip, DALL-E 2, lots of different models that actually have multimodal capability. And so basically in this line of research, I'm trying to learn sound separation, sound synthesis, all types of like audio tasks through learning from videos. Yeah, it's a bit complicated to introduce right now, so I will go into details later. So basically we do text query, sound separation, and also text to audio synthesis through learning from videos. Cool. So I will start from talking about the multi-track music transformer. So any questions so far? Good. Okay. Yeah, let's move on. So the first project that I want to zoom into is called Multitrap Music Transformer. So it's published in ICAST 2023. So an overview is like we want to generate orchestral music of diverse instruments. Like we are aiming for more than 10 instruments. And we want to use, we proposed a new compact representation. And we are using multi-dimensional transformer to generate the music. So here is an example of what the output is like. So actually, there are a lot of different models for transformer for music generation, but ours is the first model that actually offer instrument control that you can actually assign or specify the instruments that you want to use for generation. And also we have the fastest inference speed, and also like we can generate longer samples. This is important when we are talking about orchestral music, because like orchestral music, you have a lot of instruments, and it actually caused a problem in prior work that you have so many instruments, so your representation become too long to work with transformer. Cool. So let's jump into a bit more technical details. So we basically represent music as a sequence of events, like we did for natural language processing. Basically, we have words in natural language processing, but now we have events in music generation. So these events is basically a tuple of 6 components. So we have multiple types of events. So most obvious, we have the notes, like musical notes. And we also have like structural events, just like in NLP, we have like SOS, EOS. We also have start with song, end of song, and also like start with notes in our representation. And all the other fields are actually just used for specify the note and instrument information. So here's an example how we represent music in this type of NLP friendly or transformer friendly representation. So first we have these like structural events define the structure of the whole representation. And we also specify the instrument first. So like for this song, we have 3 instruments. So we specify that we have 3 instruments at the beginning. And at the latter part, we specify all the notes that we want to generate. And so this is how we represent music in this project. And so now, once we have this representation, it turned into like a series of numbers. And so this is basically what we use transformer to generate. And so I won't go into detail, but basically it's just a transformer model, but the output is like multidimensional. We have 6 fields to predict at the same time. And it's also trained auto-regressively, basically like predicting the next event given past events, just like typical transformer model. And one benefit of this type of representation is that we can actually do 3 types of sampling modes at the same time. So first we have the unconditional generation. That's basically we put into this SOS token and then let it generate. And we can also do instrument informed generation, which is not possible using the previous representation, that we can basically specify the instrument first, because we have this like recipe then cook type of representation that we have the instrument at the first, and then we started generating the notes. And finally, we can also do continuation, like typical NLP models that you see ChatGPT is basically doing continuation mostly. And we also, we only need to train 1 model for all 3 sampling modes. And so here are some examples. We have like unconditional generation. And we also have like instrument informed generation. So basically we just want a music piece that's like composed with all these instruments specified here. Cool. And we also have like a 4-beat continuation example. Yeah, so the first 4 notes actually sound super familiar. It's actually Mozart's piece. So yeah, as you can see, like music generation is not just about like creating new stuff. It's also possible to do like this kind of like morphing or like I don't know, like transformative type of creation that you can base the output on some inputs that you like. Cool. And so also we have some numbers. So basically our model is lie in between two existing representation. It's like higher quality than triple M, but it's like lower quality than Remy plus. But the benefit is that actually it's run much, much faster, and we can generate in much longer examples. So which is like a trade-off between quality and speed. And in the final part, we also do the first like self-attention analysis for music. So basically, what we want to measure is like how when generating music, how the model attend to previous events to generate the next token. So this is the definition. So basically what it did is like, computing the mean attention weight assigned to a certain attention, relative attention. Yeah, so here is an example. When we are generating the last token, we just look into how this token attend to different previous nodes. And so for example, like here we have like two notes that's like of pitch difference of -8. So we have the pitch 73, we have the pitch 65. So it corresponds to a pitch difference of -8. And so these will be accumulated into gamma -8. And we also have like a different accumulation to different gamma, basically. So, and also this has a problem that is like biased towards difference that occur more frequently. So we also adjust that to get the mean relative attention gain. So yeah, it's a bit more mathematical, but basically what we found is like when doing this type of like attention matrix visualization, we see that the model actually learns something musically. So the first thing is that the model actually learns to attend more to notes that are 4 beats away in the past. So this is super musical because like in most of the samples that we have in our training data set, it's like 4/4 beat. So 4 beats basically means that it's on the rhythm that the music typically have. And the second thing is like it's mostly attend to the same position as the current note. So an on-beat note will attend to the previous on-beat note, and an off-beat note will attend to the off-beat note previously. And also we also see that for the pitch, the model will attend more to a pitch that actually forms a consonant interval to the current note. So all these are like a relative self-attention for music, and it actually complies to the, or like follows our understanding of music theory. Cool. So in this work, we basically propose an efficient representation and model for multi-thread music generation. And also we have the first systematic analysis for musical self-attention. Any questions so far? Sure.
Thank you for this. I would like to ask you a question. So for training a music generative model, is the loss, or how do you conclude what is a good music?
Oh,
the training data is used from music from the past, and we cannot create like innovative or new music. So.
Yeah. So for the training is basically just like negative log likelihood. So it's like how you train the NLP transformer model. So during the training, the model is just like maximizing the likelihood. And so for evaluation, what we did is basically doing subjective listening tests, because like automatically evaluating music is super hard. And there are lots of automatic like evaluation metrics for evaluating music, but I don't think like most of them is not doing the thing that you expect the model to be evaluated. So I guess the ultimate way is to let human listen to it. So basically, we will send out a questionnaire for people to listen to the different music that the different model generates and like let them rate. And so that's how we typically evaluate those. Cool. Thanks for the question. Yeah, so let's jump into the next project. So that's like more recently, more latest work. So this is this line of research is basically working on multimodal learning for audio and music. And that's going to the first project. This is not a generative AI project. It's for source separation, but it's like tightly related to the next project I will be talking about. So this is an internship work I did last summer at Sony. So basically what we want to do is like learn text query sound separation with noisy unlabeled videos. So before jumping into the details, I want to briefly introduce what CLIP is. So it's called Contrastive Language Image Pre-training. So basically, this is a pair of encoders. We have the image encoder and text encoder, and together they are called CLIP. And so how this model is trained, it's basically if we have a cat, like an image of cat, and we also have a text of cat, and we pass through these two encoders, and we will get the embeddings out. And also, if we have a dog image and also the text of dog, we will also get a pair of embeddings. And our goal is to make these embeddings similar. So we want to make the image embedding of cat image and the text embedding of the word cat close to one another. So basically, once we've done this training, we will have like a joint embedding space for image and text. And this whole framework is called Contrastive Learning. And in addition to making that closer, we also actually make all the different pairs further away, like making cat image far away from dog image. Cool. So basically, once we have the clip, we have a shared embedding space for image and text. So how this can be useful? So as we talk about, so we want to do text query sound separation. So the ultimate correspondence that we want to learn is from text to audio. And it's super hard to learn this because like there are few text audio pairs for training data. So in this work, we are basically using the visual domain as a bridge. So image in the center, we have the clip model that offer us a bridge between text and image, because we have the vision language models that have a shared embedding between text and image. And for image and audio, it's much easier to get the data because like every video has the naturally occurring audio visual correspondence. And so basically image and audio correspondence is like a free, we have free data in all the videos. So no text audio pairs required, and we also can be scalable to large video data sets. So why don't we use text audio pairs? So at the left, we have the text image pairs that used to train the DALL-E 2 and all the like Midjourney model that you've seen recently. It's like 5 billion text image pairs. But for audio, unfortunately, it's only 0.6 million. So that's why we haven't seen like large training on text audio generation. And so in this project that we just want to propose an alternative way of training the model that we can use YouTube videos. It's like huge amount of data. And if we can use that to learn text to audio generation or text query sound separation. Cool. So this is how we are going into the details. So the model is called ClipSep. And so we are doing source separation here. So basically, we want to separate the sounds from the mixture of sounds. So how we train this model is basically we take two videos and we just sum their audio track up. And our goal is to separate the two sounds from the mixture. And so this is how we train the model. And so basically, our goal is to pass through this like audio UNet model and generate a bunch of masks, and then magically, we want to generate the two source, two spectrogram mask that can be applied to the regional mixture to get the sounds out. And this is through condition on the image that we have. So basically the model, what the model is doing is actually looking into the mixture, and then you listen to different sounds, and then basically it's like doing a classifying. It's a classifier that's trying to classify each pixel into whether it's the sound from the first image or the sound from the second image. So that's how we train this model. And so here we are using the CLIP model, image encoder as the encoder. So the benefit of using CLIP is that because we know CLIP offers a shared embedding space for image and text. So we can actually switch to using text as inputs at the test time. So basically, when training, we are doing image query. So we use the image to like inform the models, like which, to basically condition the model to do the source separation. But at the test time, we just do a zero-shot transfer into text query. So at inference time, we are using the text like a photo of playing, I don't know how to read it, but playing some instrument as the query to get the output. Cool. So we work on two data sets. One is like instrument playing videos, and the other is like more noisy videos on YouTube. Cool. Here are some examples. So we have the mixture here, and our query is playing harpsichord. So let's listen to the mixture first. And so this is the output. And this is the ground truth. So as you can hear, we actually hear some of the, coffin sounds in our output. So that's the part that we actually do another innovation here. So we also propose another method called noise invariant training on top of the model that I just showed. So it makes the image, makes the figure even more complicated. But I won't go into details. But basically now we are doing more than source separation. We are also doing noise signal separation. So now we have like 4 outputs. We have like signal 1, noise 2, and signal 2. So it's basically doing more disentanglement in noise and signals. And so this is based on the assumption that noise channels are interchangeable between sources. And so this whole training process doesn't require any clean audio to train, but we can actually achieve better noise suppression. So now the output, by using this technique, we will get something like this. Yeah, so you actually even make the sounds, the noise sounds less like presented. Cool, and also we can see on the numbers that we actually see significant performance improvement when we are using the noise invariant training. And what's cool is that even though our data sets are all noisy data, we can actually achieve noise removal in the zero-shot setting. So here we have the input mixture. It's like a super noisy, like it's a person playing a bagpipe on a Las Vegas street. So it's super, super noisy. And this is what the model generates. So you can hear that all the background noise are actually automatically being pushed to the noise head that we have. And let's listen to the noise head. So yeah, so we can learn this type of like noise suppression using just noisy data. So in summary, we are doing like text query, sound separation using only unlabeled videos. And we also propose another noise invariant training for doing this using only noisy data. Cool. So this is not generative AI, as you probably noticed. It's like source separation, but this is based this is the foundation of the next research I want to talk about. So basically, we can apply the same idea into audio synthesis. So here we are doing like using videos to learn text query sound separation, but we can also use videos to learn text to audio synthesis. So as the Clip Sonic will be published in WASPA 2023. So this is an internship project with Stoby. Yeah, so a bit more background. So I've already introduced Clip, and now we are also need the diffusion model. So yeah, just go through the diffusion model quickly. So diffusion model is a type of generative model. Basically, we have some image, and we just apply adding noise gradually for like T steps, and it's like mostly large T, like 1,000 steps. So at the end, it will become just like a pure noise image. And the idea is that we train this diffusion model to remove the noise gradually. And so, so at the generation time, basically we just put into the model a bunch of like noisy images, and the model will try to remove the noise gradually. And then after 1,000 steps, it will magically become something like recognizable. So diffusion model has been super successful in like image generation, and we are wondering how we can apply this to generate audio. And so that's what we did in this project. So similar to what we did in the previous source separation model, now we are basically doing image to audio generation first.
So the idea is to have a diffusion model that works on spectrogram. So basically, spectrogram is a 2D representation, time frequency representation of audio, and we find that we can actually use diffusion models on spectrogram as treating them like an image. So, so this process, this diffusion model is actually conditioned on the image input, because we are doing image to audio synthesis during the training, and this image is encoded by the Clip model. So we basically condition this diffusion model with Clip image embedding. So once again, like because we are using Clip model, we can actually switch to text during the inference time, because Clip is a shared embedding between language and images. So during the inference time, now we have a text input, say a photo of train whistling. So we pass through the Clip text encoder, and we will get a Clip text embedding for our text input. And actually, we find that this doesn't generate good audio output with our diffusion model. So we find that we can actually introduce another diffusion prior model, which is also used in the DALL-E 2 model. It basically transferred the text embedding of Clip text embedding into Clip image embedding, and it drastically improved the performance of the diffusion model. So here's an example of the inference time. So again, similar to typical diffusion models, we pass in a bunch of input noises, and it will gradually remove the noise and becomes something recognizable. So listen to one of the example. So this is the input. It's basically noise. Now, after 900 steps, this is what it sounds like. And this is the final result. So somehow the model did a lot of job at the final 100 step. Cool. So similarly, we do this on the music and VGG sound dataset, which is like music instrument, high quality playing videos, and also noisy videos with diverse sounds in the wild. So here are some text to audio synthesis demo. So we fit into the model these texts, and we want to get the audio that correspond to these texts. So here are some examples. So yeah, as you can hear, most generated audios are actually corresponds to and follow the text that the user specified. And also we also show like we have significant performance improvement against the baseline through a subjective listening test on both data sets. And also interestingly, because we are doing this type of like transfer learning across modality, like during training time, we are actually working on image to audio synthesis, but at inference time, we change to text input. So the byproduct of this process is the image to audio synthesizer. So here's some demo of that image to audio synthesizer. Cool. So interestingly, even though our goal is not to get a powerful image to audio synthesizer, we are interested in text to audio synthesis. It actually achieved the state-of-the-art image to audio performance then. So we see a significant improvement in the fidelity and also competitive relevance score with our image to audio synthesizer through a subjective listening test. So to sum up, we propose a text-to-audio synthesis model that requires no text-audio pairs, and we achieve strong performance and in subjective listening tests, and we also achieved surprisingly state-of-the-art performance in image-to-audio synthesis. So to conclude this part of research on multimodal learning, basically what we've done is to use the image or the visual domain as a bridge to learn the desired text-audio correspondence. And this offers us two benefits. One, no text-audio pairs are required, which are super hard to get. And it's also scalable to large video data sets. And lastly, I want to point out that I believe there's a lot more to learn from videos, and because videos basically provide free audio visual correspondence. It's like you go to YouTube videos and you watch all the movies, or humans in real life just look into the real life scenes and learned a lot about the world. And so there are a lot more richer context information and temporal dynamics that we are not currently leveraging to learn our desired, say, text to audio synthesis or even cell separation. Cool. So in the final part, I would like to talk a bit about some future direction of generative AI for music and audio specifically. So I see three challenges. First, we have the multimodality issue. So I believe take music generation system, for example. Text to music generation it's not the end. Like if you ask a musician to think about what's the ultimate user interface or the input interface to control the system, it's probably like a mixture of different modality. Like I want to use text to control our generation. We also want to put in reference music track or audio or like image to show what we want. And also like maybe we could condition it on like video or emotion curves. So basically the possibility that if we can get multimodal interface at the input side, it would increase the drastically increase the usability and controllability. And so that links to the second challenge that I see as basically the usability. So by usability, I mean how user can interact or use these tools naturally. Professional content creators don't want something that's like a magic button that get everything done automatically, and then that's it. Like you cannot edit it. So by usability, our goal is to achieve or to provide something that's human usable, like human can step in and change some of the parameters and to control the output. And the final challenge is on the licensing. So this has been an ongoing discussion, and I don't think there's a solution yet. And people are still trying to see what's the best way to actually license copyright materials for training a large generative AI system. Cool, so that's a bit to give you an idea what I mean for each challenge. So for multimodal generative AI, I usually work on 3 domains: text, image, and audio. There are plenty more, but I will focus on these 3 at this time. So as we see, there are several different tasks that are relevant to some of the intersection between different modality. We have like text to image generation, editing, and also text to audio generation and editing. And we also have like image to audio generation and audio to image generation. But there are a lot more. Like in the middle, we can say something like text to video generation or like text controlled video editing. And there are just a lot more to be explored in the middle part. So remember at the beginning, I showed the video generation example for the India city, like a tourism video. So now I can also show you another example of like an advertisement for whiskey. So the video is generated by Runway Gen 2. And the music is generated by MusicGen, which is a state-of-the-art music generator. Cool. And finally, I also want to show you another example of like news generation. So this is a collaboration between BBC and a group in UK. So basically, what they want to do is to use AI to generate news automatically. So here's the prompt given to the system. So basically, they just say, generate an audio in science fiction theme, Mars news reporting that humans send light-speed probe to Alpha Centauri. So everything else is actually generated automatically by some AI system. So the script is generated by GPT-4, and also how these different audio composed into the final audio is also generated by the GPT-4. And then they use MusicGen to get the music, use Spark to get the narration, use Audio LDM to create the sound effects. Let's listen to the demo.
Welcome to Mars News, your source for interstellar news and updates. We have a significant development to report today. Humans have sent a light-speed probe to Alpha Centauri. Now, let's connect with our on-site reporter to give us a brief overview.
We're here at the headquarters of the United Earth and Mars Government Space Exploration Division, where the probe was developed. And we're speaking with the chief engineer responsible for this groundbreaking project.
Thank you. So it's a fantastic achievement for humankind.
Cool. So basically what they did is like, you have the instruction and they use the GPT-4 to generate this something called audio script. So it's basically a table that shows like from which time in from which time to which part of the video that you want, what kind of music or speech or sound effects. So it's a table that shows the start, onset, offset, and also the content to be generated. And they then use the pre-trained generative audio models to actually render these sounds into the final audio that you just listen. So this actually provides us a very nice interactable intermediate outputs that you can actually edit those. So imagine like this can be integrated into professional creative workflow. So like in Premiere Pro or other video editing tools, this table is basically corresponds to the timeline that you see in these software. So imagine in the future, like you have the AI system that can automatically generate the storyboard. And if you can step in and change some of the lines, like the narration or even like the timing for each event, it will drastically improve the controllability and usability of these AI systems. So this is just one example of how controllability and usability can be achieved through using large language model. And so finally, for licensing, I don't think there's an answer yet. People have been exploring and discussing with different fields. But I would like to show an example of Adobe Firefly. So basically, it's the first model or first system that's being trained with royalty-free Adobe stock images. So this is different from other image generator, which are mostly trained on like unlicensed images scrapped from the web. And so I guess this is like the future of how licensing could possibly work out for generative AI system. Say you have to talk with the copyright holder to achieve an agreement how we can use their works to train our generative AI system. And so I guess we will see more and more of this type of collaboration in the future. Cool. So all the projects that I show, it's not my single person work. It's through collaboration with multiple researchers at different institutes. And thanks for funding all the projects. Cool. So I would like to end this talk with this cool AI generated art. So this is generated also by Adobe Firefly. And it's probably something like robot playing musical instruments on the stage. And so as you can see, generative AI has already been like revolutionizing humankind and how we produce art, produce content, and also like work. And so with that, thank you so much. I hope you enjoy and learn something from the talk.